Hello, everybody. Nice to see you all, and it's a beginning of a new week. Happy Monday to everybody. I hope that this staying at home hasn't gotten too much to you, but my hope is that also that you've had a chance to maybe explore different ways to learn and maybe even meet a different community. Actually, one of our hopes with doing this daily live stream is that we can also build a pretty interesting community. And I see we have over 100 people here already joining us for today. Some of you have been here before, some of you have not. I can usually tell who has been here before or not based on whether people are talking about the color of my shirt. Yes, indeed, the high temperature over here in Pittsburgh today is in the 60s, and so that's why I'm wearing a short sleeve shirt. But at the end of the day, somehow the shirt that we wear is not as important as what's inside, and so my hope is that we'll have something interesting to talk about. Now, if you're new to this session, I just want to give you a brief welcome. What we'll be doing here is very different from your usual math class because you already have a usual math class. You don't need to look at me for the usual math class. You have your teacher. What I try to do is I try to give something else. And the something else, which you'll see, is a discussion that kind of ranges over lots and lots of different topics. Math is, of course, at the center of them. However, math is the tool and the powerful idea, the force that unites all of the ways to work on these different subjects. So this talk and this whole live stream they're gonna move all over many, many different topics. However, we'll try to focus on topics that are basically in Algebra 1 or Geometry, or understandable to people who are in Algebra 1 or Geometry, because we understand that that's where most of our audience is coming from. Now, if you've been here before, you are probably knowing that every single live stream is going to be different. And what's this one going to be about? I don't know. It depends on what you guys ask. So what questions do you have? I'm looking forward to improvising on some of the questions that you ask to see what we can discuss for today. I see. Okay, so let's start with Pi. Pi asks, what is the law of large numbers? The law of large numbers is that numbers can get as large as they want, and there's no limit. No, that's not what you were looking for. The law of large numbers is something that has to do with what happens if you maybe look at the average of something. If you're doing something over and over and over again, that the average somehow seems to be closer and closer to a particular number. What do I mean by that? Well, if I go and look at a person outside in the world and ask, how tall is this person? Well, who knows? Maybe I found a baby. That person's pretty short. Or maybe I found Shaquille O'Neal. That person's pretty tall. Actually, if the two were standing right next to each other, well, then that might be an average person. Well, maybe a little bit shorter than an average person, but I'm just simply saying that somehow you can start to measure averages as you do things. But you see, if you just went out once and found just a baby, and you said, well, my average height of everyone I've ever seen is, I don't know, like 1.5 feet. That wouldn't be very interesting. On the other hand, if you're doing this longer and longer and longer, you'll notice that your average seems to be converging to a number. And that would be the average height of a person in the population. So I think maybe what you're going for is something about, law of large numbers. Maybe if you look at enough things, the average becomes close to the actual average. And that's a really powerful fact. In fact, that's how you do statistics. That's how you even do things like figure out what % of people are likely to vote one way or another way. You don't have to ask everyone, just because of the fact that the average of who you've asked so far is converging to what the actual average is. Other questions? Let's see. What else do we have here? I like this. Shireen Zhang asked, is math more about logic than just memorizing facts? Yes, it is. That's how I think about math. And that's how I've been doing all of these live streams. My hope is that you've observed that whenever we're trying to answer any kind of math question, it's not, oh yeah, that's how it is. This is the way to solve the question. I remember. No. It's much more interesting to go and use logic to puzzle your way through it. And the sooner you learn how to do math through logic instead of through remembering facts, the easier math will be for you. What other questions can we have here? I like how some people are asking whether other people are here yet. That makes me happy. That means that you've built a community. What else do we have? I see somebody asked, is Novid on the App Store yet? No, we haven't solved that problem yet. We're still trying. But we're not going to give up. Talk about Novid. Let's wait until a few more math questions first. I want to make sure that we talk about enough math here because this is supposed to be a math live stream. Grandfather paradox. Oh, I see. Okay. I see some of these things. You know what? I'm not exactly sure what is the grandfather paradox. That might be something about, but that's like a twin paradox. But I saw something else. I saw something called, I think you wrote Simon's paradox or like Simpson's paradox is probably what you meant. That's kind of fun. Let's talk about that. All right. So here's the deal. I'm going to tell you that something has happened that's quite interesting. You see, this is about baseball. Let's suppose that we have some kind of a baseball, what's it called? A baseball league, that's what it's called. So we have a baseball league, and we have a bunch of matches in the first half of the season, and a bunch of matches in the last half of the season. And let's suppose that we know something pretty interesting. We got one person who is like, let's call that person A. That's a very inventive name. But person A, in the first half of the season, has a higher batting average than person B. Person A has a higher batting average than person B in the first half of the season. By the way, what does batting average mean? Batting average means that you got ready to bat. I guess this is just a pen. But anyway, you get ready to bat and you try to swing, and I guess you guys, it's sort of like successes over attempts or something like that. Probably. Oh, what is the question? The question is, Yitong Li, the question is something about a paradox. And so I'm telling you a very interesting paradox. You came just in time. All I'm saying is that in the first half of the season, when person A was batting, compared to when person B was batting, person A's batting average was bigger than person B's batting average. That's true in the first half of the season. And also in the second half of the season. Okay, so here's the fundamental, very important question. Who has the higher batting average overall? This is the easy part. All right, this is the easy part. This is the easiest question. Look, person A has a higher batting average than person B in the first half of the season, and person A also has a higher batting average than person B in the second half of the season. So for the easy part of the question, who has the higher batting average? Person A? Yes, of course. Of course it's person A, right? And how do you prove that? Well, you see, that's what math is about. So math is about proving something. This is like some obvious fact. Duh, exactly. And Andrew Chow is asking, what is a paradox? Well, the paradox is that it's not person A. What? Let me show you. Let me show you an example. Okay, so we're going to make the first half of the season and the second half of the season. And here's what I'm going to do. I'm going to say that person A is here. Person B is here. I'm leaving some space because I want to write overall. Okay? I'm going to draw an example of something that could happen. So person A had a higher batting average than person B in the first half of the season. And person A did that by having one success out of 100 attempts. Let's call it 99 attempts. Meanwhile, in the first half of the season, person B unfortunately had 0 successes. Divided by, person B was mostly a bench warmer. Person B only took 1 attempt. So it's true, in the first half of the season, person A's batting average was higher than person B's batting average, right? 1 over 99 is bigger than 0 over 1. Now, in the second half of the season, here's what happened. person A's batting average is still higher than person B's batting average. Person A made one success out of one attempt. So basically, person A finally just decided to give up on baseball, all right? And just say, I'm just going to do it once. But they got a home run. Uh-oh. Meanwhile, person B became like better than Babe Ruth. Person B became a superstar. Person B made 98 successes out of 99 attempts. Okay, in the second half of the season, look, person A has a higher batting average than person B, 1 for 1, 100%. Meanwhile, person B, not quite 100%. You know, they missed one. Uh-oh. Now I see a lot of people saying, oh, wait a second. So in this case, what happens for the overall? How do you figure out the overall batting average? The overall batting average, what do you do with these fractions? Do you add the fractions? What should you do? So let's look at the first row, person A. What is the overall batting average of person A? They got one success for 99 attempts for the first half, and then one success for one attempt for the second half. Do you average them? Is that right? Do I take 1 over 99 and average it with 1 over 1? Not quite. What would you actually do? How does it work in baseball? What would you say is the overall? How many successes out of how many attempts? Multiply, divide? Actually, this is the weird thing. Yes, you add numerators and denominators, what you're not supposed to do. This is not how you normally add fractions. But this is 2 total successes divided by 100 attempts. What that means, by the way, is that the overall batting average for person A is an extremely lousy 2%. Maybe I could even do better than that. Oh man, person A is so good, right? Better batting average than person B in both halves. And a 2% overall. Meanwhile, I see that somebody has already figured out what is person B's overall batting average. 98 successes. Oops, success has 2 C's, doesn't it? Divided by 100 attempts. And person B has something that goes into my head, 98%. Okay, so, oh no, who has the better batting average overall? It looks like it's person B in this case. Of course, it doesn't have to be that way. Sometimes the answer is person A, sometimes the answer is person B. Effectively, what this shows is that the batting average for the first half and the second half are not enough to tell you conclusively who has the higher batting average overall. There are, of course, examples where person A actually gets the better batting average overall, if you had better in the first and better in the second. But it's not guaranteed. And this shows not only is it not guaranteed, it could sometimes be way off. Not just a little bit off. Person A should just quit baseball. Meanwhile, person B, it must be cheating. Like, how in the world do you get a 98% batting average? Must be cheating. So, okay. So that has a name. This whole thing that we've just talked about has a name. It's called Simpson's paradox, because it was first taught on The Simpsons. No, that's actually not true. But it is still called Simpson's paradox. Okay, more questions. What else can we talk about? Let's see. What do we have here? Must be cheating. Yes. So I see some questions. Some of these are a little bit easier to talk about quickly. Some of them are a bit harder to talk about quickly. Luke Wang asks, what is standard deviation? Standard deviation is something which, I'm not going to give you a mathematical definition of it, but let me give you an idea of it. So suppose what I did is I said, let me go and see how tall everyone is in the world. And I go run around and I find out that I need to draw some kind of a chart. Charts usually look like this. You might have seen charts before that look something like this, where you say, all right, I've got some buckets. Maybe here is the average height of a person. Sorry, when I say here's an average height of a person, what I mean is that maybe this is between, I'm in America, but let's just say it's between 5 feet and let's call it 5.5 feet. Actually, that's probably not an average height of a person, is it? Well, whatever. I can always make a taller thing later. But maybe it's like this. And what these bars mean is they're sort of counting how many people have a height between 5 feet and 5.5 feet. And then there's the 5.5. And then, it just keeps going. And, there aren't that many, there are less people between 6 feet and 6.5 feet. So this is now at 6.5. From 6 feet to, from like 6.5 feet to 7 feet, I think it's a lot less people. How many people are over 7 feet tall? Now it's pretty few. This is like at 7, like over 7 feet tall. That's like pretty few. Maybe you can barely see it. And does anyone know anyone who's taller than 7.5 feet tall? Yeah, that's getting very, very little, right? Meanwhile, I can go the other way. As I go the other way, here's the people whose height, maybe these are adults. How many adults are there whose height is between 4.5 feet and 5 feet? Well, actually, that's quite a bit less. And if you want adults, oh no, that's not supposed to be a vertical axis. Let's get rid of that because that's not 0. But how many adults have height between 4 feet and 4.5 feet? Now that's quite a bit less. And we got a picture that looks like this. So this might actually be roughly correct. I mean, I'm making this up based on my own experience, 6.5, so this goes up to 7.5. This is based on my own experience walking around in the world. Yao Ming might be tall enough. I actually don't know how tall Yao Ming is. I just know he plays basketball, and all those basketball players are out here. Do you know who's out here? Actually, here's a question. Does anyone know? So like there's a certain sport for which it's very, very good to be tall, which is called like every sport, like swimming, like basketball, and so on. Does anyone know any sports where it's really, really helpful to be a very small person? There's actually a value. There are some sports where they really are looking for small people. Does anyone know what they are? Ping pong. Ping pong is an interesting idea. I'm not sure. Gymnastics, that might be interesting. I mean, gymnastics, it might make you able to have a lot of this core strength. Wrestling might help. Soccer, swimming, interesting. So epee fencing, interesting. I see all of these different things. I love how David Tsiang said hide and seek. You guys are great. Okay, but in any case, I mean, actually another sport that is a real sport is like horseback riding. I think if you're a jockey, like if you're the one riding the horse, you better be pretty small because you don't want to be as heavy for the horse. I saw somebody said limbo, right? So there are benefits to going onto this side. And also there's another sport in the UK called crew, or like when you row a boat. Now, of course, if you're doing the rowing, you better be huge. But there's always somebody who sits at the front of the boat trying to make sure that the boat is steered and also telling people like what to do. That person is not helping to row, so they should be as small as possible. Okay, anyway, so like this is like the spectrum. Now when I talk about something that looks like this, like the fact that this is a bigger chunk just means there are more people with a height between 5.5 and 6 than there are between 5 and 5.5. I'm actually not sure which way is supposed to be bigger. But in any case, there's something called the average or the mean. And the mean is the number that is sort of like the average of all of these. It's as if you took the average of every height and you said that's the mean. Now there's something else here called the standard deviation. The standard deviation is roughly speaking like about how far away from the mean you need to go so that on both sides you pick up about 2/3 of the whole distribution. Like the thing that I drew looks sort of like this. Looks sort of like this. And that's actually what happens whenever you take a lot of independent things and average them together. Now, in this case, it also happens that in real life, you see this thing called the normal distribution a lot. Maybe that's even why it's called normal. But somehow there's something in the middle, which is the mean. And then you can say, about how wide is it? Like it's useful to know, for example, would somebody be really extreme if they were just merely 8 feet tall? Yes, apparently yes. But if we were talking about heights of trees, we would be like, no. The trees don't have heights just ranging between 4 and 8. It's like somehow you can have these super, super tall trees as well. And there are also some really short trees, right? There's a notion of like, how wide is the spread? And the standard deviation helps you to measure. It's called the deviation. And it's called the standard deviation. Each of these yellow things is approximately 1 standard deviation away. So what you should think of is in this part, like corresponding to the stuff in the middle, that's about 2/3 of everything. So what's in the middle is about 2/3 of everything that's inside that we happen to have. Like it's about 2/3 of all people are within -1 standard deviation and +1 standard deviation of the average. Actually, I think it's 2/3. I don't exactly even remember. Maybe there's someone here who has taken statistics who can help me confirm. Is it actually correct that one standard deviation below to one standard deviation above is like 2/3 of the mass? If there's someone here who can help me double check that fact, that would be great, because we've got lots of people watching this live stream. But that's vaguely what I seem to remember. And so the bottom line is somehow between these, this is just asking, like, how far do you need to go so that between this one and that one, you pick up about 2/3. So yes. Okay, so that'll be my answer to standard deviation, and you could calculate it with some formulas too, but it's useful to know, roughly speaking, what we're talking about. Is standard deviation related to mean absolute deviation? That's a question by John Liu. So technically speaking, not exactly, but since this is now more sophisticated than what everyone's asking in the Algebra 1 and Geometry levels, I'll just tell you the standard deviation is the square root of the mean squared deviation, which is not the same as the mean absolute deviation. Those are different things. Okay, more questions. Oh, somebody said you are right, so maybe I got right. That's good. And oh, by the way, standard deviation is not exactly 2/3. It's like roughly 2/3. Okay. Oh, wow. Okay, so I see Rosie Hong asked a very interesting question. How to know if a number is prime or not? So, let me give you a number. It's my favorite prime number. My favorite prime number is 91. How do you know if it's prime or not? What should you do? So I'm telling you, how do you figure out whether 91 is prime or not? Well, you start dividing it by stuff, right? You go and say, can I divide it by 2? Can I divide it by 3? Can I divide it by 5? It doesn't work, so it's obviously prime, except that all of these people are saying, no, it's not prime. 91 is my favorite number, which looks prime, but is not. So unfortunately, 91 is not prime at all. And I like to give that example so that you don't make that mistake. By the way, 97 is prime. But how would you know? In fact, the way that we usually check to find out whether this is prime or not is exactly to go and test dividing it by all of those numbers which are smaller than it. But you can save yourself some work. You only have to divide by prime numbers. You don't have to check. Like if you already tried dividing 97 by 3, then if you try to divide 97 by 6, of course it won't work, because it didn't divide by 3, and dividing by 6 is harder. So I'll just advise that, if you want to check if a number is prime, go and, divide by all these numbers which are smaller than it, that are also prime. Of course, there's a deeper question, which is it possible to test whether a number is prime or not, and how easy is that? Those are more sophisticated. I myself am actually not a specialist in that area, but the people who care a lot about cryptography to make sure that your communications are safe on your computer, those people think a lot about these questions. More questions. Have you had an IMO student who is better than you at math? Life of Yushen Gaming. Oh yeah, all of them. Actually, they better all be, or else we're in trouble. I'm not actually that great. I mean, what I'm trying to say is that the next generation, the future, people are always better than the people who are the past. I think that's a good thing. We should always hope that as a civilization, the next people that come forward are more capable and able to have a greater impact than the people who were there before. We always want to improve. So generally speaking, all of the IMO students I work with are more intelligent than me in mathematics. And that's a good thing. And I guess what I try to do is I try to show them a few things that if I happen to know, it's not because I'm smarter, it's just because I've been around longer, so I can maybe share some mathematics that maybe they hadn't seen yet. Can you take off your glasses? I did that last time, but it's the same. It looks the same. Okay, let's see. What else do we have here? Oh, how did you choose the daily challenge color blue? Amy Fan. That's a deep question. So the way we chose the color to be blue is because the daily challenge is actually made by XP. So XP is a social enterprise. It's an organization that I founded about 6 years ago to try to help the world through math and education, and apparently now also through stopping COVID-19. But that organization, XP, happened to have the color blue because we wanted to choose a color that it wasn't blue and it also wasn't purple. It's sort of like both at the same time. I guess to me, I always enjoy things that are kind of a blend between two things. Like even the shirt I'm wearing, it's not exactly clear whether it's blue or whether it's purple. I actually like these kind of ambiguities Because whenever you have two things fusing together, it's kind of beautiful. And you can kind of change your perspective as you wish. So the color for XP has always been this bluish purple. And so when the Daily Challenge was founded to make these online math classes that not this thing, but the systematic online classes that are also on our website, those Daily Challenge classes all got the same theme color of blue. And actually, that's also why Novid, if you look at our app to stop COVID-19, that is also the same shade of blue. So it's all of these are just somehow a beautiful shade of blue/purple that has a little bit of ambiguity inside it. Okay. Huh. This is interesting. So I see. So I see a question by Rong Hong Lin. How many atoms are in the Earth? Wow. How many atoms are in the Earth? Okay. So for me to try to figure that out, how would I figure that out? I guess I could be way, way, way off. I'm going to say there's a couple of different ways that one could hit this. And yes, you're watching me think, because I'm like, there are a couple of different ways that I could hit this. One of them would be to attempt to use volume, and one of them would be to attempt to use mass, both of which are interesting and legitimate. So the way I would do this is that, let me just go ahead and start playing, okay? I'm going to start playing with volume, okay? So if I want to play with volume, what could I do? So, and by the way, I think we did mass. Did we do, I think we already did mass. We did the mass of the Earth at some other point. But the thing about the mass of the Earth is I'd have to use something else. But if I wanted to know, like, based on volume, what did we know? We knew that the volume of the Earth was going to be, well, again, this is going to be a way, way, way off approximation. I just want to know roughly where we are, right? So, okay, the radius of the Earth, at this point we've done enough of these problems that I'm going to say it's like 4,000 miles. We've seen this kind of problem come up enough times in the live stream to say it's going to be about 4,000 miles. Fermi problem, here we go. Let's see what happens. So if it's a 4,000 mile radius, first thing I want to do is convert to kilometers. And the reason I want to do that is because the width of an atom is an angstrom, which is 10 to the power minus 8 meters. So that's roughly what I want to use. I want to say that somehow atoms are about 10 to the minus 8 meters apart. An angstrom, I think an angstrom is 10 nanometers. That's like what I'm thinking about, okay? So there's something about like the atomic scale is about 1 angstrom. I think, by the way, if we have a physics teacher here, please correct me, or a chemistry teacher here, please correct me. I could be wrong on this. I'm just basing on like my vague understanding of the world. And that is about 10 nanometers, I think. I remember it's either it's 1 angstrom is 10 nanometers or 1 nanometer is 10 angstroms. I vaguely remember that an angstrom is bigger. But anyway, let's keep trying, okay? If it's 10 nanometers, a nanometer is 10 to the power minus 9, and that would be 10 to the power minus 8 meters. So let's see. You're saying an angstrom is a tenth of a nanometer. Okay. So in that case, maybe I'm off. So let me double check with the audience. It's a tenth. So okay, thank you. So what this is showing is that somehow I remember there's this tenth going on, and so it'd be one or the other, one way or the other. Let's go the other way. So it's 10. Okay. The good thing is we can use negative exponents. 10 to the power minus 1 nanometers, and that gives me now 10 to the power minus 10 meters. Okay. So now what I'm going to do is I'm going to say, let's go and pretend that we've gotten like a bunch of, atomic scale, by the way, is like, that's roughly how big, and like atoms can be measured in those units. Now the question is like, is it like 1 atom is 1 angstrom across? I don't actually remember. We could be way off, but it's like, yeah, it's around that scale, okay? So then what I'm going to do is I'm just going to say, let's go take the volume of the Earth and divide it by the volume of a cubic angstrom. Right, and that would be like somehow giving me some vague idea of how big, that would be one of the atoms, and we've got all of this volume of the Earth to pack everything together. And so if I've gotten this, let's see. So I've got 4,000 miles. 4,000 miles in kilometers is approximately 6,000 kilometers. Okay, and now what I'm going to do is I'm going to go and take 4/3 pi r cubed to go and figure out what is the volume of the Earth. Okay. So the volume of the Earth would be 4/3 pi is 22/7 times the radius cubed 6,000 kilometers in terms of meters is actually 6 million meters. 6 times 10 to the 6 cubed. And that's going to be the volume of the Earth. So this is the volume of the Earth. In cubic meters. And then what we're going to do is we're just going to convert it into cubic angstroms and see where we are. Okay? This is 4/3 times pi. Pi is the 22/7. Okay? So let's see what happens. If I go and do this, what are we going to get? Well, we're going to get, I don't know, what's the easiest way to do this? I see 4 times 22 is 88. 3 times 7 is 21. 88 divided by 21, that's about 4. 6 cubed is 216. 10 to the 6 and then cubed is 10 to the 18. So this is about 4 times 216 is about 1,000. So that's about 10 to the power 21 cubic meters. Okay, so if I was going to go and make a random guess about the atoms, what I would say is, I've got that many cubic meters. Let's convert that into cubic angstroms, because we're going to say that somehow in each meter, we're going to have 10 to the 10 by 10 to the 10 by 10 to the 10. And so what that's going to be is that's going to be 10 to the power 21 times 10 to the power 30 cubic angstroms. And I'm sort of saying like that's like an atom, okay? And again, this can be way off. So then what do we get? We get that this is about 10 to the power 51 atoms. Okay, what's the actual answer? Now I'm actually going to look at what the chat says. What is the answer? How many atoms are there in the Earth? I'm a little curious now. I mean, like I could have been way, way, way off. I'm just sort of using this. How many atoms are in the Earth? Scientific notation, please. So what is this? Could you please use scientific notation with like times 10 to the power something? Because I can't actually count all of those zeros. So, you know, like that's why we don't use zeros. Are you joking? 1.33 times 10 to the 51? That's what I wrote! Whoa. Are you serious? It worked! Okay, so that's not bad. Actually, it turns out that it's pretty close. I'm surprised. Okay, I'm actually surprised it worked that well. You guys aren't just playing with me, are you? So, okay, I see enough different people are saying that. So it's like ding, ding, ding. Okay, by the way, let's just see again like how this worked. The way this worked is I made a mistake. And so there was a mistake here. You guys helped me fix the mistake. But this is where I'm showing that like the value is to know roughly like how big things are. That's not a bad thing. It's like, so it's nice to know that like somehow an atom, there's an atomic scale. I knew there was a 10. It was either like 10 nanometers or like a tenth of a nanometer. You also, by the way, saw that I hesitated and I was like, are you sure? Am I sure it's this way or maybe it's the other way? But it's somehow there's this tenth thing over here, right? But once you know that that's how big one atom is, you just go and use your volume to go and figure the rest of it out. Okay, good. Well, that actually worked. I'm surprised. Okay, more questions. Wow, you guys are asking so many of these interesting questions. What was your worst grade ever? I don't remember. And I mean, what I mean by this is that somehow it's like, so you know, I did try to do school carefully, right? So I did get A's. But I mean, at the end of the day, it's like, you know, A is an A. What else can you say? But I think my whole goal with school, I'll just say it in a different way, is that somehow the goal was to go and make sure that if I have a teacher in a classroom, you know, you are doing whatever the teacher has asked you to do and do it well. And so if you just keep doing this, you probably won't have that much problem with grades. So yeah, the answer to your question is actually they were quite good. But you can get good grades, just don't overstretch yourself. And, you know, if a teacher asks you to do something, go and do it well. Okay. More questions. Oh, PE, yes. PE is a very important class to do well in also. Actually, if you want to make sure that you're a healthy person, you can't just be good up here. Okay. Okay, let's hit some other of these questions. I'm just looking at all of these different pieces. I see somebody is asking about the square root of -2. Let me hit that. I just want to make sure we have a nice balance of like some questions which have math and some questions which don't. So the square root of -2 is very hard to make because I can't take the square root of a negative number. If I multiply two real numbers together, even if they're both negative, minus times minus is plus. So that's not useful. So actually the square root of -2, the way to think of that is this. let's first think about what happens when I take the square root of a number like 36. You see, the square root of 36, what is it? Well, I mean, many people can say it's 6, or maybe it's minus 6, depends on your perspective. Although if you write it this way with a square root sign, that actually refers to the positive square root. So it's going to be 6. Whenever you write the radical sign like this, it is 6, not minus 6. But now, there's another way to think of the square root of 36. That's equal to the square root of 4 times 9. Now, the square root of something times something is always equal to the square root of the first thing times the square root of the second thing. And there's a good reason for that. Because look, if I took this, root 4 times root 9, and I multiply it by itself, what happens? Well, root 4 times root 9 times root 4 times root 9, that's equal to, you can multiply in any order that you want, and you can multiply the root 4 by root 4 first. Root 4 times root 4, and then times root 9 times root 9. And so that's going to be equal to just 4 times 9. And so therefore, this root 4 times root 9 is also the square root of 4 times 9, which is what's here. Okay, and then we just do that normally. That's equal to 2 times 3. Now you asked me, what do you do with the square root of minus 2? For the square root of minus 2, you split it the same way. You split it into the square root of 2 times minus 1. And now if I split it into the square root of 2 times minus 1, then I'll get the square root of 2 times the square root of minus 1. Now, unfortunately, you cannot take the square root of minus 1, but that's why we defined a number as a complex number, an imaginary number, that you can use to be the square root of minus 1 to do more useful calculations. And that's I. So this is square root of 2 times I. So that's the square root of minus 2. That's actually, yes, I see Jiang Michael has said this is square root 2 times I. And that's how you would usually simplify something that says square root of minus 2. I should add that somehow when you write something like this, I had previously said that this radical is always the positive one. That's always the positive square root. There are, by the way, 2 different numbers whose square to minus 2, whose square to minus 2. And those 2 numbers are root 2 times I and minus of root 2 times I. Which one of those is the positive one? That's a good question. It's actually not completely clear to me what positive I means or negative I means. But the good news is that usually when you see root of minus 2, you don't see it standing there by itself, because it's not a real number. In fact, this sort of thing usually comes when you say, what are all of the different solutions to some equation? And at that point, usually there's a plus or minus in front of this, at which point there's a plus or minus here already as well. What else can we do? Can you use math to predict the weather? I love math. Well, yes. I mean, what else would you use to predict the weather is what I would say. Weather is one of these things that has the most sophisticated models out there. The simplest model for the weather is just to say, look at what the temperature was in the last few days and see if it's following some kind of a trend. I mean, if I wanted to predict the weather, I mean, there are lots of different ways I could predict the weather, but one way might be I could just go and say, well, what has the weather been over a few days? If here are the days, and this is Monday, and this is Tuesday, and this is Wednesday, and this is Thursday, and I have another thing which is somehow the temperature. If I know that on Monday the temperature is like, I don't know, 60, these are Fahrenheit, and if Tuesday the temperature is like 61 and Wednesday the temperature is 59, what do you think the temperature would be Thursday? Probably not 0. Right? That would just be weird. So it's probably not that way. And so what you would do is you could do something very simple, which would just be to say, yeah, maybe it follows some kind of a model. And then you can get more and more and more sophisticated. You can go and say, well, yes, fine, this is what's going on, except that it's going towards summer. So it should actually start to go up. So you shouldn't just kind of follow this trend. And what you do there is you go and say, well, what was the temperature last year? And you go and see that actually as the temperature goes through the year, it follows some kind of a seasonal pattern, and you try to use that there. That's also math. Now, if you want to get even more sophisticated, that becomes how you predict hurricanes. It's like, and that's actually very important. It's that whenever you have a hurricane, you see that there are all these different warnings saying, where's the hurricane going to go? And that's significantly more complicated. On the one hand, you could say, well, all of these are like water molecules, and these water molecules, just simulate all of them. They all follow the laws of Newtonian mechanics, which is to say that when something is in motion, it will stay in motion until somehow it runs into another object, and maybe they bounce off, and you can go simulate. Except that we don't have a computer big enough to do that. And then we use math to go and try to find a way to summarize some of that information. So you won't suddenly go and say, I need every single particle covered, but maybe like this bunch of particles I'll try to cover in some way. I'll say this bunch of particles has a certain density, has a certain mass, and is moving in some direction. And all of this is using math. So, in fact, math is the fundamental tool in predicting all of the weather that you see today. Looking at all of these different questions. So I saw somebody ask a question about kites. So I guess it's about weather. You know, like how do you prove that the diagonals of a kite meet at right angles? So first of all, you need to know what a kite is. I can do this real quick. That's pretty easy. So when I say that's pretty easy, what I mean is, I think I have an explanation that I might be able to make for you that I have not actually tried ever before. So let's try. Okay. So let's draw a kite. What's a kite? A kite is an object which is symmetric around the middle. That doesn't look symmetric. It's symmetric around a line that goes through the middle. You know, like a kite. That's a kite. And I just told you it's a quadrilateral which is symmetric around the middle, around one middle line. And that is the only thing, if I remember correctly, about a kite. It just has to be symmetric around this. Oh, it has to be symmetric. Well, if it has to be symmetric, then that means that this point needs to reflect over to that point. Right? That's the symmetry. And so if it has to reflect over to that point, then, well, it goes through at a right angle. So that would be a right angle. Okay. Now, if what you wanted is something that would be more suitable for your geometry class at school, that one might not be sufficient. You might say, your teacher might say, I'm afraid that all you said was it's symmetric and therefore it's a right angle. That is, by the way, how we think when we write these Math Olympiad proofs. Oftentimes, if you're writing Math Olympiad proofs, it's okay to just go and say, well, by symmetry, I have this perpendicular. But when you're learning geometry for the first time, that's not what you do. In fact, we have to even think about, in geometry, what is the definition of a kite in the first place? Let's get rid of this first, since I don't yet know whether it's a right angle. So in a geometry class, I'm not exactly sure how you guys define kites, but I wouldn't be surprised if the way that kites are defined in geometry class is that you say, I've got two sides which are equal in length, those are called congruent, and I've got two other sides which are equal in length, which are also called congruent. That tick is not as obvious, I'll do it here. Okay? So this would be a kite. It would be a quadrilateral for which I've gotten those two lengths to be the same and those two lengths to be the same. Now the question is, why is there a right angle? And if you look at this, the way that a lot of proofs in geometry go is they start to go and reason one step at a time. And so let's first look at part of the top. I want to isolate my attention on the part of the top that looks like this. And you'll notice I'm drawing a new fresh picture. The reason is because as you draw these fresh pictures, you can stare at them and you can notice interesting patterns. Hey, look, I've got these two sides which are the same. Can anyone tell me what else has to be the same if I have two sides of a triangle which are the same length? Can anyone tell me? What is the question? The question is why in a kite, which is this kind of object, why do the diagonals cross at a right angle? So if I look over here, angles, thank you very much. Crazy Vishnu. Wow, we got a crazy person here. And that's a crazy good answer too. So if you've got these two which are the same length, then actually that means the angles are the same length. So because of what I started with, now I also know that these two are the same. The angles aren't length. These are the same size. The base angles are the same measure is what we call it. So let me go back over here and label them. Okay, that's one thing I can do. There's something else that you can do in geometry also. Something else you can do in geometry is something called congruent triangles, which is called if I've got two triangles where all of the sides are the same, then where all the pairs of the sides, sorry, this side is the same as that side, this side is the same as that side, this side same as that side, they're called congruent. And if they're congruent, then all the parts of those triangles are also congruent. Let me focus on two congruent triangles for you. One of them looks like this. That looks a little bit lopsided, but I hope that it's understandable what I'm drawing. I've just separated apart the kite. Now, what I just said about what I just said about congruent was that if I've got two triangles for which all the pairs of the sides are the same length, then I'll be okay. Aha! Temp ID says use SSS congruence. Right, that's the sides. See, those are the same. These sides are the same. Hey, how do I know that these two blue sides are the same? Oh, they're just the same. They're the same thing, right? Those are the same side. All I did is I just took the kite and I pulled it aside. So of course they're the same. These two are the same, of course, because they were just the same side. Now, once I have congruent triangles, meaning that the sides, this is called SSS congruence, it's what you learn in geometry class, but you don't need to really think about those names, it just makes sense. It's like, look, if these two are the same, then now suddenly some angles also have to be the same. And the angles I'm going to draw that are the same are up there. Those two are the same. Okay, now we're almost done. Because let's go back and take this picture and put it over there. If I put it back over there, then I have that this angle is the same as this angle. Now my claim is that we could figure out why this angle is a right angle. Why is that? Well, what do I actually have here? I have those two are this, like this green is the same as that green. I also have that this pink is the same as that pink. CPCTC, wow, Ivy Hood, we still use CPCTC? That's what we used when I was growing up too. Corresponding parts of congruent triangles are congruent. I think I remember that. Okay, so now let's put this together. So I now have like the green angles are the same, the pink angles are the same, and I'm now going to use, you just said there's something called angle-side angle congruence. This is also true. That wasn't what I was going to use, but that's just as well. Let's use that. So if I use angle-side angle congruence, then I can say that the top part, if we have here, right, this is the top part. I'm going to make some triangles. This is the other part of the top part. We've gotten this thing. This is not necessarily a 45, 45, 90 right triangle. Just looks like one, but that's not the important part. These are the same. These are the same. And these are the same. And if you try to draw a triangle which has a side of that exact length and make an angle out of it which is the green one and an angle out of it which is a pink one, it will have to look like this. And so it's congruent. Because it's congruent, because these two are congruent, now I also know that these two are the same. That means that these two are the same. Now, can someone tell me why they're both equal to 90 degrees? If I have that this angle and that angle are congruent, meaning they're the same size, why do they add up to 180 degrees? Oh wait, I just gave it away. Oh no, they add up to, they're both 90 because there are two equal numbers that add up to 180 degrees on a straight line. So each of these is exactly half of the 180. So that's the reason. So each of these is exactly half of the 180. So each is 90 and 90. And that shows why, if I draw a kite, these diagonals intersect at a right angle. This is the very, very, very detailed proof that goes through every single step. The intuitive proof is, well, it's a symmetric thing, and it reflects across one of these axes, or across one axis. However, what I had said first would not cut it if you were trying to hand it in school. But this is what would work. Okay, what other questions can we have? Are you overwhelmed because of all the questions? Says lol candy. I think the questions are really interesting. I'm not overwhelmed. I think it's very interesting to go and see all of these different questions come out. It's really fun to also see that people are talking. What else do we have? Okay. So I saw somebody asking things like, you know, why is Fibonacci so common in nature? And my easy answer to that is because it's the easiest way to say what you'd build next. Like when the easiest thing to do is to say, well, build this thing and then build this thing and build something which is the sum of those things. It's a very simple instruction. And when you think about nature, nature needs to have a lot of order and it has to be organized with as simple instructions as possible. So I think that's why. Actually, if you think about it, there aren't that many other simple instructions. Like one simple instruction is called, if you have something, then after some minute of time, make sure you have the same thing. And after some minute of time, make sure you have the same thing. That's called a rock. That's not very interesting. Except for erosion, it might have less stuff. Then there's something else, which is called, I have something. And then a minute later, I have two of the same thing. And then sometime after that, each of those becomes two of the same thing. And that's called like bacterial growth. It's like multiplication in that sense. And the Fibonacci is just a very slightly more sophisticated way of not just times two, but it's just whatever I had before and whatever I had right before it, combine those two to make something new, which is the next one. Okay, what else do we have here? I'm trying to look at all of these. What's the fastest way to find out how many factors a number has, says Shireen Chang. That is best suited for like an actual math lesson. So I'm sorry, that won't quite fit into this particular live stream. We actually do that in our official course, but I'd rather not just use that time to hit this. I'm trying to hit as many like non-course things as possible if I can. Continuing to look through all of these different questions. How good is your memory? Came a question. Not perfect. I mean, you just saw. It's like my memory, I didn't have this thing correct about which is bigger, angstrom or nanometer. But I sort of knew there was a 10. So you can see like the whole way that I recommend for people to learn things is have a bunch of facts that you can connect between. So that you don't necessarily have everything just remembered as one fact, one fact, one fact, but there's the whole connection between all of them. And then that way, you don't actually need to have an amazing memory in order to yourself solve some hard questions. Oh, this is cute. I see a question. No Name has asked this question. Hexagons in nature. I like that question a lot. Because there are hexagons. Why do we see hexagons in nature? Well, these things come up often. Hexagons come up when you do some kind of a beehive. So the idea is that there are certain patterns in nature that can repeat. And so hexagons are one of them. And so that's actually quite natural. Also, hexagons are quite efficient in other ways. It's like if I wasn't talking about a beehive, but if what I was doing is I was making cookies. Maybe you've done this before. Has anyone tried baking cookies before? And when you bake cookies, how would you put the cookies on the sheet? Do you make your cookies this way? Is that how you make your cookies? This is like quite normal. You make the cookies this way. But when you make the cookies this way, then that has somebody has cookie emojis too. But if you make the cookies this way, that sort of wastes some cookie area in the middle. And, that's maybe not optimal. So the question is, could you try to maybe put your cookies on the pan in a better way? For a rectangular pan, this might not be bad. Unless the rectangular pan is huge. So there's a certain situation where it's like, if the size of the cookie is small enough, it might not be good to do this. So with like giant cookies, well, normal size cookies, on a normal size baking pan, you do make them this way. On the other hand, imagine what would happen if you had a giant baking pan. What if your baking pan was like this big? I guess that would mean that your oven was the size of your house too. But anyway, that aside, let's just say you got this giant baking pan. And furthermore, imagine you were making mini cookies. Like mini cookies. See all these mini cookies? They're the same size. It turns out that if your cookies are that small, and all of these are like, and this like this pan is that big, you shouldn't put them in this rectangular pattern. You shouldn't just put like all of these cookies like a normal rectangular pattern. It turns out it's better to pack them like the beehive. So that's where the hexagons are coming in. It turns out that the significantly better way to do it is to pack in your cookies where you're making the circles like this, and you do this in between. Now if you look at where the pattern of the centers of the circles are, that's exactly where the centers of the hexagons are in the beehive. So who knows? Maybe the bees are busy making honey cookies. Well, probably not honey cookies. They are definitely making honey. And in general, this is showing how some of these things, like hexagons, can even be optimal. Like in this case, it appears in nature, but it's optimal. So you said, I see that Aaron Peng said square is best. Square is best if you have big cookies and a reasonable sized baking pan. And if what you're trying to do is to put the most area of cookies down, then that would be the best. On the other hand, if you have a smaller size cookie compared to your baking pan and you're putting them down, if you want a denser batch of cookies, you're actually better off doing this way. The reason why it makes sense when you squeeze everything down to do it this way is because you don't lose as much on the edges. So you see, the problem is like if I went over here and I said, hey, I have a better way. Look, watch how smart this is. We can make our cookies like this. That looks terrible because you can't even fit any more cookies here or there. You see, it's wasting on the edges. So the point is that this particular kind of packing, it's wasteful on the edges only, but in the middle, it uses much, much better. So like if you look at how little space there is in between there compared to putting the cookies like in a square pattern, the square pattern leaves a much bigger hole. On the other hand, the hex pattern leaves a much smaller hole. So in the middle parts, it's more effective to use the hex pattern, but you lose out on the borders. And that's why, if what you end up doing is you end up looking at a gigantic sheet, like a gigantic baking sheet, well then the middle stuff is the most of it. Like the borders are just a tiny, tiny, tiny part of the whole system. The way to think of this is, has anyone ever done those like 5,000 piece puzzles before? I don't know if you guys like doing puzzles, but they're like 2,000 piece puzzles. I can do like a 16-piece puzzle. But some people sit down and go and do a 500-piece puzzle, a 5,000-piece puzzle. And at that point, you've got these huge, huge, huge puzzles. And the first thing you do with a giant puzzle is you put down the border. But if it's a 5,000-piece puzzle, you put down the border, and it looks like you haven't made much progress. It's like just somehow all these pieces are around, and that's it. And there's nothing else in between, inside the middle. So, oh wow, it looks like Musical Element of Life did a 2,000-piece puzzle. That's quite an accomplishment, actually. But you see, that's why I'm talking about it with the baking sheets. The deal is that if you have a puzzle and you filled in the middle, the middle is most of it, is most of the pieces. And so at this point, if you have a giant sheet and small cookies, you should switch to the beehive type pattern. It looks like, unfortunately, we're basically on the last question. So let's choose something which is maybe like a fun random thing. Haha, this is kind of funny. Why do people always count sheep when they try to go to sleep? Says Dubby Math. That's a good question. I wonder if it's because a long time ago, maybe people actually had to count sheep. Maybe they were shepherds, and you want to make sure there's the same number of sheep as in the morning? I don't know. I should say, actually, in my life, I'm not sure I've ever really been up close to a sheep ever. That might be true. I don't think I've ever actually been up close to a sheep. And so I wouldn't even know what counting sheep looks like. I just know these like cartoon pictures of sheep. So I honestly don't know. It's probably because people who wrote these children's books, maybe they had it about sheep because maybe people were farmers or shepherds or something. And that might make sense. And that seems like a good way to say, I see somebody said ba. I suppose that's sort of like bye. But unfortunately, that will also be the end of today's live stream. Real pleasure to have the chance to talk to you all today. And please do try to help bring more people in. That's going to make it more fun for everyone. And then hopefully we can, instead of counting sheep, let's count people. Wish you all the best and have a great day.